Okay, this is the answer key to reactions in aqueous solutions, problem set 3. First question, if you want to double the concentration of a solution, how could you do it? Well, since the formula for molarity is equal to moles of solute over liters of solution, you could do this a couple ways. You could either double the moles of solute, or you could reduce the volume of the solution by half, as long as you keep the moles of solute the same. So one of the ways you could do that is by just letting some of the solvent evaporate. Question 2. Calculate the molarity of each of these solutions. So 5.623 grams of sodium hydrogen carbonate, and we're dissolving that in enough water to make a volume of 250 milliliters. So again, we know the formula of molarity is moles of solute per liter of solution. I'm going to go ahead and find moles of solute. 5.623 grams of sodium hydrogen carbonate. And I know that 1 mole of sodium hydrogen carbonate has a mass of about 84.01 grams. And this is all in a volume of 250 milliliters, which comes out to be 0.2500 milliliters. Now, every measurement that I have there has 4 significant digits, so I'm going to leave my answer as 0.2677. And the unit on that is capital M for molarity. Second question, 184.6 milligram sample of potassium dichromate is dissolved in enough water to make 500 milliliters of solution. So first thing, I have milligrams instead of grams. And these simple conversions between milliliters and liters and milligrams and grams, you don't necessarily have to show those. And if you know exactly how many grams or how many milligrams are in a gram, just go ahead and do the conversion and write that out as 0.1846 grams. And that's potassium dichromate. So probably the hardest part of this is actually looking up the formula for potassium dichromate. So it's K2Cr2O7. And we're going to change that to moles. So 1 mole of potassium dichromate has a mass of about 294.2 grams. And again, I'm going to put that over the volume in liters, so 0.5000 liters. And again, both of my measurements have 4 significant digits. So we're going to get 0.001255 molar, or 1.255 times 10 to the negative third molar. Last question for number 2, we've got a 0.1025 gram sample of copper metal. It is dissolved in 35 milliliters of nitric acid. And then what they're doing is they're adding water to get a total volume of 200 milliliters. So watch this question, because the actual volume we're working with is our final volume of solution, which is 200 milliliters. We want to calculate the molarity of copper plus ions in that final solution, not in the 35 milliliters. So our concentration is going to be the 0.1025 grams of copper metal, which has all been converted to copper 2 plus ions, and their mass is going to be really the same. The 2 electrons that are being given off from the copper atoms to turn into copper 2 plus have no bearing on the mass whatsoever. We know that 1 mole of copper has a mass of 63.55 grams. And we know that our final mass here is going to be 0.2000 liters. Again, everything here has 4 significant digits, so 0.008065 molar of copper 2 plus ions, or in scientific notation, 8.065 times 10 to the negative third molar copper. All right, let's take a look at question 3. Oh, I left that all off screen. All right, take a minute and write that down. I didn't realize I was solving that off the screen. All right, let's take a look at 3. Describe using lab equipment and calculations how you would prepare 250 milliliters of a 0.70 molar sodium nitrate solution. Okay, so you have to remember some of the equipment, and I know this is normally a first year lab, so using a volumetric flask is normally something you would do in first year. Using a pipette is something you would do in first year. So in order to make this solution, we need to know how many moles we need to add. So there's a couple different ways you can do this. You can go back up and you can use that formula for molarity, plug this in for molarity, plug 0.2500 in for volume, and then solve for moles. I'm going to use dimensional analysis. And really, if you can see this using dimensional analysis, it kind of helps with a lot of different problems if you can't quite figure out what formula to use. So I know I want moles, and I know molarity is really moles of solute per liter of solution. So I'm going to take my 0.2500 liters of solution that I want to make, and I'm going to go ahead and multiply that by 0.707 moles of sodium nitrate for every 1 liter, because that's my molarity. So I'm just going to turn my molarity right into a conversion factor. Get rid of liters when I do that. And then to figure out the mass of sodium nitrate I need, I'm going to go ahead and use molar mass, which is 85.00 grams of NaNO3 for every 1 mole of NaNO3. So that tells me I have to mass out approximately 15 grams of NaNO3. So if you think about hopefully the vodcast you watched on over the notes, you're going to actually dissolve the 15 grams first in a 250 milliliter volumetric flask. Okay, and that's a flask that's has only 1 graduation mark on it, and that's exactly at 250 milliliters. You're going to add distilled water. Just enough to dissolve your 15 grams of sodium nitrate. And then what you're going to do is you're going to add more distilled water until you get to the graduation mark. So add distilled water to dissolve, and then to the mark. And then you're going to mix well by inverting several times. Okay, and that's pretty much it. Remember the volumetric flask, that's kind of an important piece of glassware. It is the most precise piece of glassware that we can use to actually measure out exactly 250 milliliters of a solution. All right, let's go ahead and let's move on to problem number 4. All right, the average adult human male has a total blood volume of 5 liters. The concentration of sodium ion in this average individual is about 0.135 molar. What is the mass of sodium ion circulating in the blood? So we're looking for mass, which means we know we're looking for grams. Again, dimensional analysis. We're going to take, and we know molarity is moles per liter. So I'm going to take my 5.0 liters of blood. I'm going to mark that off so I know what I'm talking about. And I know the concentration of sodium ion I want is 0.135 moles of sodium ion per liter of blood, because that's our solution. Okay, so in other words, if I have 5 liters, I'm multiplying that 0.135 moles of sodium by 5. Now, again, we talked about ions, right? A sodium ion is going to have the same molar mass as sodium. So that's going to be 23.0 grams of sodium ions for every 1 mole of sodium ions. And watch what happens here. Liters cancel, moles of sodium cancel, and I'm left with mass. We get about 15.525 grams of Na plus. Because my 5.0 has 2 sig figs, I'm going to go ahead and round that to 16 grams of Na plus. Okay. All right. Not too bad. This one's a little bit different. A person suffering from hyponatremia. That's interesting. That's actually where the symbol comes from there. Has a sodium ion concentration in the blood of 0.118 molar and a total blood volume of 4.6 liters. What is the mass of sodium chloride that you need to add to bring the sodium ion concentration up to 0.138 molar, assuming no change in blood volume? So, first thing that we need to do in this case, and this really, there's a couple different ways you can solve this. The first thing I'm going to do is I'm going to figure out how many moles of sodium I have and how many moles of sodium I need. And then I'm going to use that to help me figure out how much I have to add. So if I have 4.6 liters of blood, and I know that I have 0.118 moles of Na plus for every 1 liter of blood. That's going to give me 0.5428 moles of sodium ion. Okay, I'm actually going to keep track of sig figs here. I usually draw like a little arrow. Since this has 2 sig figs, I'm going to kind of just write 2 sig figs there or keep track of my sig figs there. Now I'm going to go ahead and figure out what I need my moles of sodium to be. And so we want, this is my have, what I want is I want in 4.6 liters of blood, I actually want 0.138 moles of Na per liter. So that's a 0.6348 moles of Na plus. There's my sig figs. So I'm going to take the difference between those. So I'm going to subtract, I'm going to take my 0.6348 moles and I'm going to subtract 0.5428 moles of Na plus. And the difference between those is about 0.092 moles. Now here's where sig figs come in. If this is a sig fig and this is my last sig fig, then I can't be any more precise than my least precise decimal place, which actually ends up being right here. So I'm kind of keeping track of that. This one's a hard one for sig figs. It would not be on the AP exam. So what that means is that's how many moles of sodium ion I need to add to bring my concentration up to the 0.138 moles of sodium. So since I know the formula for sodium chloride right here is NaCl, that also means since I have a 1 mole of Na plus for every 1 mole of NaCl, I need 0.092 moles of sodium chloride as well. So I'm going to take my 0.092 moles of sodium chloride, and I know the molar mass is 58.5 grams of NaCl for every 1 mole of NaCl, and that gives me 5.38 grams of NaCl that I would have to add to the blood to bring my sodium ion concentration up to where I want it. Now, this is where I was talking about sig figs. Since this is my last sig fig in this measurement, there's only one significant figure there. So it would be appropriate to say 5 grams of NaCl. Although, again, I would not take points off for sig figs on this one. So when in doubt, go 3 sig figs, and usually you're pretty safe. But this one was a tough one with sig figs. Okay, on to question 6. Indicate the concentration of each ion present in the solution formed by mixing 42 milliliters of a 0.170 molar sodium hydroxide and 37.6 milliliters of a 0.4 molar sodium hydroxide. So the thing that you have to remember is that whatever your concentration is of that compound, when that compound dissociates or when it dissolves, that concentration actually will dictate your concentration for your ions as well. In both of these solutions, I can see that I've got a 1-to-1 ratio of sodium ions to hydroxide ions. So in other words, what I'm saying is when sodium hydroxide dissociates, it dissociates into an Na plus ion and a hydroxide ion. And so whatever my concentration is of my sodium hydroxide, that's going to match my concentration of sodium and hydroxide ions. The difference is that I'm mixing them together. So my final molarity is going to be my total moles of Na plus or OH minus over the new total volume. So probably the best thing to do here is to figure out my total moles. So I'm going to go back to my molarity calculation. So I'm going to go to solution 1. In solution 1, I have a total of 0.042 liters of sodium hydroxide. And I've got a concentration of 0.170 molar NaOH for every 1 liter. This is actually going to give me 0.00714 moles of both Na plus and OH minus, because I have that 1-to-1 ratio that I was talking about. So however many moles of sodium hydroxide I have, that's the number of moles of Na plus and OH, because it's a 1-to-1-to-1 ratio. So for solution 2, I've got 0.0376 liters of sodium hydroxide. And this time I have a higher concentration, 0.400 moles of NaOH per liter. So that's going to give me 0.01504 moles of both Na plus and OH minus. Now, keeping track of significant figures, I'm just going to throw this in here really quick. This has 3 sig figs, that has 3 sig figs. So here's my last significant figure there. 1, 2, 3. There's my last significant figure there. Now, I want the total concentration. So remember, I need the total moles of Na plus and OH minus. So I have to actually add both of these numbers together. So when I add my total moles together, I get 0.02218 moles. And that's of Na plus or OH minus. There's my last significant digit there, but it doesn't matter because I'm not done. I'm not done yet, because to solve for molarity, I need my total moles, which is 0.02218 moles. There's my last sig fig, over my volume. Now my total volume now is my 42 milliliters plus my 37.6 milliliters, but in liters. So when I add that together, I end up with 0.0796 liters. Divide that out, we get 0.2786 molar concentration of Na plus and The same for OH minus. 3 significant figures would mean I'm going to round there. So 0.279 molar Na plus or OH minus, since everything's a 1-to-1. Now, they didn't ask you for the total concentration of all your ions. They asked you for each ion. So watch out what they're asking for, because if they ask for your total concentration of ions, you would have to then double that because you've got Na plus and OH minus. All right, let's take a look at question number 7. Oh, wait, do we have more on 6? Sorry, 6B. Oh, why did I put so many questions on here? No, I'm just joking. You're probably asking the same thing. All right, here we go. On this one, we have 44 milliliters of a 0.1 molar sodium sulfate solution and 25 milliliters of a 0.150 molar potassium chloride solution. We have no ions in common here. So we're going to figure out the molar concentration of the sodium ion, the sulfate ion, the potassium ion, and the chloride ion. And we're going to kind of do this the same way. The only little twist that we have here is the fact that for every 1 unit of Na2SO4, we're going to produce 2 Na pluses and 1 SO4 2 minus. And so you have to remember that because the concentration of Na plus is going to double that. So let's take a look at solution 1 first. So solution 1. So I'm going to solve this one a little bit differently. Since I have no ions in common, one of the things that I can do is use M1 V1 equals M2 V2. And the reason that we can use this, and the only time we really can use this, is if moles of our ion are not changing. And since we're not adding any different ions in here, or since we're not adding similar ions at all, the only thing that's going to change the concentration of, let's say, my sodium ions is the fact that the volume is going to go up. And so this particular formula comes in handy when you're doing a dilution. And in this case, since I have no common ion, all I'm really doing is diluting my ion concentration. Now, you can go ahead and solve this one just like we did with A, but I want to show you something a little bit different with this one. So what I'm really trying to solve for here is, what's my new concentration of my ion if I dilute it? And so just really quick, my final volume, I've got 44.0 milliliters plus a 25.0 milliliter. So my new volume is going to end up being 69.0 milliliters. Now, again, I'm going to keep my volume in milliliters because that unit's actually just going to cancel out. So watch what happens here. I'm going to solve for my new molarity for my sodium sulfate. So my new molarity for my sodium sulfate is really going to be M1 V1 over V2. And so I'm going to get my original molarity, which is 0.100 molar, Na2SO4, times my original volume, which is 44.0 milliliters. And I'm going to put that all over my new volume, which is 69.0 milliliters. See what I mean by milliliters canceling? And it's fine if you go ahead and you put it in liters, but it's going to cancel anyway. Now, when I solve this, this is going to give me a new molarity of 0.06377, and that's my molarity of Na2SO4. There's my final sig fig, by the way. However, since this breaks down, like I said up here, into 2 parts sodium and 1 part sulfate, my concentration here is going to be the same as my sulfate, but I have to double it for my sodium. So therefore, I'm going to get 0.0638 molar SO4 2 minus. but I'm going to double that and I'm going to get 0.128 molar Na+. So that's what happens when I dilute solution 1, when I add them together. Now we're going to do the same thing for solution 2. Now in solution 2, we've got KCl, which is a 1-to-1 potassium and chloride ion ratio. So I just really have to figure out what my new molarity is. So my new molarity is going to be my old concentration, 0.150 times, capital M, times its original volume, which is 25.0 milliliters, divided by the new volume, which is 69.0 milliliters. Milliliters cancels, and I end up with 0.054348 molar, and that's KCl. 1, 2, 3, there's my last significant digit. Since this breaks apart into just K plus Cl minus, my concentration of K plus and Cl minus both end up being 0.0543 molar. That's it. That's all of them. So not having a common ion actually makes it a little bit easier to do this calculations if you think about it in terms of just diluting. Okay, so for this one, we're back to having to look at it kind of a little bit differently because we've got common ion in here. So one of the things I'm going to do with this one, since I'm really just taking my 3.60 grams of KCl and putting it into a solution that's already made at 75 milliliters. What I want to do is I want to figure out what my concentration is going to be of my KCl in that 75 milliliters. I also could just find out how many moles of KCl I have and do it that way too. So there's a couple different ways to do this one. You could convert everything to moles, add your moles together for your common ion, and divide by 75 again. I'm going to do this a little bit differently again. I'm going to figure out what the concentration is just of my KCl when I put it in my 75 milliliters of solution. So remember, molarity is just moles of solute per liter of solution, and they're telling us our volume of solution is 75. So we've got 3.60 grams of KCl, and I know that 1 mole of KCl has a mass of 74.55 grams of KCl. Now, my volume is going to be 0.0750 liters. So that's going to give me a concentration of 0.6439 molar KCl. 3 sig figs are going to stop about right there. So I'm going to round that a little bit. So therefore, I've got 0.644 molar K plus and 0.644 molar Cl minus. But I've got some chloride coming from this other compound. Now, since I already know the concentration, I've got 0.250 molar calcium chloride. I know this is going to break down into Ca2 plus and 2 Cl minuses. So that's going to give me a concentration of 0.250 molar for my Ca2 plus, but I'm going to have twice the concentration for chloride ion, so 2 times 0.250 molar for my Cl minus. So that's going to give me 0.500 molar Cl minus. So I've got this concentration for Cl minus, I've got this concentration for Cl minus. I have to add those together. So my K plus, I'm going to rewrite this, is 0.644 molar. My calcium ion is 0.250 molar, but my chloride ion is going to be the 0.5 plus the 0.644. So that's going to be 1.144 molar. Cl minus. There we go. So 3 slightly different ways to take a look at it. So figure out kind of what works for you. Now let's move on to dilutions. So in the video or in lecture or however we went over this, you know a stock solution is the more concentrated solution. So they want to know how many milliliters of the stock solution you're going to need to dilute to make 1,000 milliliters of a lower concentration solution. So here's what we're going to do for part A. We're just going to use that molarity of our stock solution times the volume of our stock solution is equal to the molarity of the more dilute solution times the volume of the dilute solution. So again, moles of ammonia, we're not going to change the moles by diluting it. So we can use this formula because moles stay the same. Remember, molarity is, and let's take a quick look at this. Since molarity is moles of solute per liter of solution, I'm going to rearrange this. And so I'm going to get moles equals molarity times volume. I'm just going to do M1V1. If this doesn't change, if moles is the same in situation 1 as it is in situation 2, then M1V1 is going to be equal to M2V2. Boy, I'm running out of room there. Okay, so that's how this actually works. If moles stay the same, then we really can say, hey, my initial molarity times volume is going to be equal to whatever my new molarity is times my new volume, as long as the moles are not changing because we're just diluting it. So what we want to solve for is what volume of stock solution we need to take out of our stock solution with our pipette. So Vs is equal to our dilute molarity times our diluted volume divided by our stock solution. So hopefully it makes sense. We definitely need to take way less stock solution out than what we need to make. Okay, it doesn't make any sense to take more than 1,000 milliliters out and dilute it to 1,000. So this number should always come out hopefully as a lower number. Otherwise, you did something wrong. So my diluted solution concentration is 2.50 molar. And I want to make 1,000 milliliters of it, which is just 1 liter. I'm going to keep all those significant digits. So 1, 2, 3, 4 zeros. So 1, 2, 3, 4 liters. And my original concentration is 14.8. So you can see molarity cancels out and I'm left with liters. So again, we could have used 1,000 milliliters and kept our unit liters. It really doesn't matter. So when we calculate this out, we actually get a volume of 0.01689 liters, or about 16.9 milliliters of, let's see, stock solution. We'll just say stock solution. All right. Now the second question says, if you take 10 milliliter portion of the stock solution and dilute it to a total volume of 0.5 liters, what will the concentration of the final solution be? So we're going to use the same thing for B. We're going to use the molarity of our stock solution, which is 14.8 molar. And we're going to actually only take 10 milliliter portion. I'm going to leave it in milliliters this time. We're going to dilute it to 0.500 liters, which is 500 milliliters. But we want to know what the new concentration is. So that's what we're looking for is MD. And this is going to be 500 milliliters. See what I did there? I just took my liters into milliliters. So make sure those units are the same because milliliters will cancel. Molarity, will be the only one left. And so we get a concentration of 0.296 molar NH3. That's it. So make sure your units for volume are the same. Otherwise, that can really mess you up. But when you're using this formula, it doesn't matter if you keep it in liters or milliliters, but they have to be the same. All right. Let's see. Oh, wow. Last page. Number 8, starting with sucrose. Describe how you would prepare a 250 milliliter of a 0.25 molar sucrose solution. Describe how you would prepare another solution with, okay, here we go. All right, so for this one, we are going to, number 1 for A, we need to figure out what mass we need to measure out. So I know that I have 250 milliliters that I need to make, and here's my concentration. Remember that this is moles per liter for concentration. So I'm going to take my 0.2500 liters of solution I'm trying to make, and then convert to moles and convert to grams. So 0.250 moles of sucrose. I can spell it out every time. Per liter of solution. And the molar mass of sucrose, because you've got the formula there, is 342.3 grams. I'm going to use sucrose, SU, for every 1 mole of sucrose. So that tells me I'm going to need to mass out 21.4 grams of sucrose. So in general, you're going to mass out your 21.4 grams of sucrose. You are going to add it to a 250 milliliter volumetric flask. Put some water in it to dissolve your 21.4 grams of sucrose. You're going to swirl it around, dissolve it all. You're going to add more distilled water, fill it up to the graduated mark, and then invert it several times to mix well. That is it. Second question on here. Describe how you would prepare 350 milliliters of a 0.1 molar solution, starting with a stock solution of 1.5 molar sucrose. So just because you have 3 liters of a more concentrated solution doesn't mean you're going to use all 3 liters. So this question, you are still trying to figure out how much of that 3 liters you're going to use. So don't be fooled by the fact that they're giving you 3 liters. You're not going to use all 3. You can't use 3 liters and make 350 milliliters. So think about that a little bit. So our concentrated solution is 1.50 molar. We don't know how much of that stock solution we're going to need. That's what we're going to calculate. But we know we're going to make 350.0 milliliters of it. And we want our new concentration to be 0.100 molar, so a lower concentration. Our volume of stock solution we need to pipette out is 23.3 milliliters of stock solution. So again, in a nutshell, you're going to draw up the 23.3 milliliters of stock solution using a volumetric pipette. And then you're going to add that to a new volumetric flask. Add to a, and it's 350 milliliters. Good luck finding that, but we'll say it. 350.0 milliliter volumetric flask. And then you're going to add water to the graduated mark, graduated, something like that, to the graduated mark. So if here's my graduated cylinder, I'm going to draw really bad. Oh, actually, oh, nope, that side's going curved. Not too bad. So there'll be 1 mark on it, and you're going to fill it right to that mark. You're going to put a stopper on it, and you're going to invert it several times to mix it. That's pretty much it. All right, question 9. Woohoo, last one. How many grams of solid silver nitrate would you need to prepare 200 milliliters of a 0.150 molar silver nitrate solution? Pretty straightforward. Let's go ahead and do that one first. We've got 0.2000 liters, and I want to find moles. So I've got 0.150 moles of silver nitrate, AgNO3 for every 1 liter of solution. And the molar mass of that is 169.88 grams of AgNO3 for every 1 mole of AgNO3. That means I'm going to need approximately 5.0964. I'm going to round that to 3 sig figs right there. So I'm going to need 5.10 grams of silver nitrate. All right. Now, an experiment calls for you to use 100 milliliters of a 0.50 molar nitric acid solution. All you have available is a 3.6 molar solution. How many milliliters of the 3.6 molar nitric acid solution and of water do you need to prepare the desired solution? Ooh, interesting. All right. So let's take a look at this. We've got 3.6 molar nitric acid. So we're going to take our 3.6 molar HNO3, and we need to figure out what volume we need. We would like to make a 0.50 molar solution, and we'd like to make about 100 milliliters of it. There really should be another 0 there, but we'll leave it. And so the volume of the stock solution I need is approximately 13.89 milliliters of the stock solution. Now, I'm looking at sig figs again, and I see the 3.6 here. So I'm really tempted just to say that this is 14. I'm going to go ahead and say that the volume of the stock solution I need is 14 milliliters. So that means the second part of this question is, how many milliliters of water do you need to add? Well, so I need 14 milliliters of stock solution. And then the rest of it should be water. So to get to 100, I'm going to take 100 milliliters minus my 14 and get 86 milliliters of water. Because those two should hopefully add up to 100. No, I did it again. Sorry, you guys. Hopefully you fast forwarded through that or something. I don't know. Anyway, you have to be careful though. Sometimes when you mix two different solutions, after mixing, they don't actually come to the volume you think they're going to because of intermolecular forces. So that's kind of a tricky question, but it should be about 86 milliliters of water. All right, hopefully that helps, and hopefully you're feeling pretty good about this. Come see me if you have questions.